Welcome everybody. We're delighted to have Professor Behnaam Aazhang with us today. I'll give a brief introduction and then we'll proceed with the colloquium. Behnaam Aazhang received his BS with highest honors, MS and PhD degrees in electrical and computer engineering from the University of Illinois at Urbana-Champaign in 1981, 1983, and 1986, respectively. From 1981 to 1985, he was a research assistant in the Coordinated Science Laboratory, University of Illinois. In August of 1985, he joined the faculty of Rice University in Houston, Texas, where he is currently the J.S. Abercrombie Professor in the Department of Electrical and Computer Engineering, and Professor and Director of Rice's Neuroengineering Initiative. From 2006 till 2014, he held an Academy of Finland Distinguished Visiting Professorship appointment at the University of Oulu in Finland. Dr. Aazhang is a fellow of the IEEE and UWECE and a distinguished lecturer of the IEEE Communication Society. He received an honorary doctorate degree from the University of Oulu, Finland, the highest honor the university can bestow, in 2017. He is also the recipient of the IEEE ComSoc CTTSE Outstanding Service Award for innovative leadership that elevated the success of the Communication Theory Workshop in 2016, an Outstanding Technical Achievement Award for consistent fundamental contributions to multi-user communication theory for wireless networks in 2017. He is a recipient of the 2004 IEEE Communication Society's Stephen O. Rice Best Paper Award for a paper with Sendorazis and Erkip. In addition, Sendorazis, Erkip, and Aazhang received IEEE Communication Society's 2013 Advances in Communication Award for the same paper. He has been listed in the Thomson ISI Highly Cited Researchers and has been keynote and plenary speaker at several conferences. Behnaam's research interests are in signal processing, information theory, and their applications to neuroengineering with foci on 1, understanding neuronal circuits, connectivity, and the impact of learning on connectivity. 2, developing minimally invasive and non-invasive real-time closed-loop simulation of neuronal systems to mitigate disorders such as epilepsy, Parkinson's, depression, and obesity. And 3, building microelectronics with data analysis techniques to develop a fine-grained recording and modulation system to remediate language disorders. Another application area of interest is developing a patient-specific multi-site wireless monitoring and pacing system with temporal and spatial precision to restore the healthy function of a diseased heart. And we are delighted to have Professor Aazhang with us here today. Thank you.
Thank you. Good morning, everybody. I prepared the talk for today, basically targeting a broad audience. I had no expectation, but I just assumed there would be a broad audience. I didn't know that it's going to be a broad audience on a ramp. It's kind of freaky, you have to admit. And, this is my title. And the question, I always like to have a title that asks a question. Can electrical engineers impact neuroscience? And the short answer is hopefully yes. And that's why I raised the question. And then a follow-up question would be, as an example, can we predict and prevent the onset of seizure in epileptic patients? Which would be a very challenging problem that could bring in neuroscientists and engineers together. And the answer to this question is no. And then that may be a little disappointing to you. But the reality is that the answer is no. But then the journey to an answer is interesting. And that's what we're going to talk about today. Try to go through this journey to see if this can be done. If it can be done, what are some possible ways to get this thing done? Now, as Behnaam mentioned, I've been working in the area of wireless communication and wireless networks for many, many years. And a few years ago, I decided to look at other applications of some of the fundamentals of signal processing, information theory, and areas of that sort. And I thought it would be fascinating to me if I sort of try to sort of bring some of the tools that we have in wireless communication to a different problem, which you can think of it as trying to understand our neurological system. all right? And this area is called neuroengineering, and it basically is where neuroscience meets engineers, basically. And to get that done and to be successful in that area, which is in medical applications, it is critical for engineers to work with medical professionals and medical doctors. And this is the list of basically neurologists, neuroscientists, and medical doctors that I work very closely with. And again, to put things in perspective, this is actually, this is downtown Houston. For those of you who've never been there, this is downtown Houston. This is not downtown Houston. This is Texas Medical Center, which is by far the largest medical complex in the world, according to some estimate. And this red roof set of buildings here that are overshadowed by the medical center is Rice University. Basically, Rice University is literally across the street from the world's largest medical center. And we don't have medical school, obviously, because we have one across the street that is not ours. And we have a whole bunch of engineers like me, and we are very interested and anxious to work with medical doctors to sort of apply some of our engineering tools. And that's where this whole thing is all about. Now, in particular, I'm going to talk about the work of two of my students that you see there circled, and my colleague who's a neurosurgeon who actually does some of these surgeries, and data comes from his lab. And these are some students that are undergraduate students that have also contributed to one of these projects that I'm going to talk about. Now, for those of you who are interested, some of the work that I'm going to talk about today has been published in these 3 different papers. And of course, it's hard to remember them now, but just Google our names, and then you could find out more about the specifics if you're interested. Now, with all of that said, let me step back for a second and sort of remind ourselves what are we interested in and what is this whole area of neuroscience. It turns out that humans have been interested in how our brain works for many, 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 many decades and centuries. And it started out from the ancient Egyptian times and then carried on over the centuries and all that. And when you think about where we were back then, very vague idea of how our brain works, we made quantum leaps in that area by discovering how a cell operates, how a neuron operates. And this is a very sort of typical picture of a cell, or a neuron in our case. And the functionality is very clear, and how it spikes and how it communicates with another neuron, all of them is very well understood. And it turns out that our brain is made out of millions and millions of these kinds of neurons, and they work together as a circuit, and then that circuit functions in many, many different magical ways. Now, it turns out that our brain, a typical human brain, has about 80 billion neurons, and each of them are very, very small, obviously. And the speed that they operate, that they communicate with each other, or they produce spikes to communicate with each other, is very, very slow compared to what electrical engineers are used to in a Pentium or other processes like that. Very, very slow. But the point is that there are huge number of synapses and links between them, and they communicate with each other quite extensively. The number of synapses or connections between different neurons have been estimated to be in the trillions, which is kind of interesting that when you put it all in perspective, that there are many of them, and they have many number of anatomical connectivity with each other. A lot of them are connected to each other. But what it boils down to is less about the neurons themselves, because they do very simple functionalities. It's all about the connection between them. And the connections between them have been categorized into anatomic connections, functional connections, and causal connections. And these 3 different connectivities are critical in understanding how our brain works, why it doesn't work, and what can we do to make it to go from an unhealthy state to a healthy state. Now, to understand how our brain works, to understand how it functions, we got to get close to our neurons. We got to learn from our neurons, and we got to find out their functionality, find out their circuits and all that. And of course, it's a very hard problem because of the skull and because of the fact that our neurons are not transparent to record from them and to learn from them. And recently, there have been multiple modalities discovered to get recordings and get close to our neurons, to learn from them and also to modulate them and to stimulate them or change their functionality. And these modalities are the good old electricity, because our neurons are basically generate electricity and they communicate with each other via electrical pulses. And recently, through light and magnetic fields, we've been able to learn from our neurons, record from our neurons. And of course, they also respond to sound waves at some particular frequencies. These are the different modalities that we could use to reach out to our neurons. Bottom line is that there are billions of homogeneous neurons that they look very similar to each other. A neuron in one that is responsible for one functionality is very much the same as another neuron responsible for another functionality. Therefore, billions of neurons, homogeneous, work together. And it turns out that that is a phenomena in nature that many people are interested in. And it's been termed emergence. Kind of fascinating. Basically, look at this particular picture. You see that a whole large number of birds flying together, each of them doing very simple things, but together they can do things that are much, much more complicated than their individual action. And this concept of emergence also has a manifestation when it comes to our neurological system. Basically, billions of neurons, each of them doing very, very simple functions, but together they can do very, very complicated tasks. Now, in terms of our understanding and our way of interacting with our brain, I would say this is where we are today. And our understanding is very limited, and it is at a very primitive stage. And where we want to go would be something like this. We want to get to that point of our understanding, how our brain works, why it doesn't work, and what can we do to make it go from a unhealthy state to a healthy state, and so on and so forth. We have a long ways to go there, right? And among the grand challenges in this area that have been noted by many different agencies and many different groups there are many grand challenges, but the one that my group is particularly interested in is this whole idea of brain circuits. You know, how circuits operate, when they learn, how the circuit changes, when they are in an unhealthy state, how the circuit functions, and what are the expectations of the circuit when it's supposed to be in a healthy state, right? And this could be implemented, or could manifest itself into a disease, or when we learn, our circuit changes, when we memorize, our circuit changes, and there are many different functionalities like that that affect our circuit. In particular, my group has been interested in these kind of problems, focusing on a number of different disorders, and trying to learn about the disorder and try to modulate the disorder in a minimally invasive way, or hopefully in a non-invasive way. These are different ideas that we had, different projects that we're working on. We're interested to learn how we learn and how different simple animals learn, and so on and so forth. And most of our projects are funded by different agencies. It turns out that there are several foundations that are very interested in this kind of area, and then they provide funding to our particular type of projects. Now, today, I'm only going to talk about one project that we are excited about, and just focus the rest of the talk on that one project. And that project is the epilepsy project. Now, it's a large crowd, but I still would appreciate it if this becomes an interactive discussion as opposed to me just zipping through my slides and just talking the whole time. Therefore, I really, really invite questions. And any kind of questions you might have, you want to discuss a point, or if something that I said that is unclear, please stop me. I'm a professor. I can talk for hours. I have talked for 6 hours straight in a day. And I can cut my, my talk really short if we have interesting discussions. All right? Please stop, ask questions. All right. With all of that said, let's focus on epilepsy as one of the application domains that you're interested in. What I did here is that I thought it would we connect better with this particular disorder if we see the list of some people out there, some celebrities that we may or may not recognize, who actually suffer from epilepsy. I had no idea that Charles Dickens was epileptic, for instance. And some of these rap singers I do not recognize, but I just borrowed their pictures from Wikipedia. And, but when you see this list, there are a number of celebrities that have suffered from epilepsy, but then most of them lived a sort of a normal life despite their disorders. And, but on the other hand, there are patients out there. There is a child on the East Coast that has about 15 seizures a day. And that is not a good life for a child, and that is sort of very disturbing to hear. But these other guys all lived a relatively normal life and survived epilepsy. Now the question then is, what is epilepsy? Let's define it more formally. It turns out that the definition of epilepsy is pretty standard. It is basically unprovoked and recurring seizure. It turns out that a large percentage of population in their lifetime go through one seizure. That's fine, and the percentage goes down quite a bit when you think about people who had 2 seizures in their lives. And then, of course, the number of patients suffering from epilepsy, which is a recurring unprovoked seizure, is much, much less than the number of population that have 1 seizure in their life. All right? And that is the definition of epilepsy. But then the definition of seizure is not standard. Seizure is basically where a population of neurons get hyperexcited and they interact with each other in excited mode for a period of time. Often neurons, when they excite each other, then the other one inhibits that so that their relationship would be much more controlled. When neurons excite each other and in return they further excite each other, get into a loop, that could be called the cause of a seizure, where they're all hyperexcited and there's no inhibition in their interaction, right? And that's the definition. That is a rough definition of what a seizure is. And then with that, there could be many different seizures. It could be a focal seizure that only one area is affected by seizure. It could be a global seizure. The whole brain is affected by seizure. For that reason, epilepsy and seizure are very, very patient-specific. Therefore, any technique, any that you can come up with has to be very, very data-driven and patient-specific procedure. All right? Now, what are we going to talk about today? What's the status of our work in my group? Basically, we are, if you want to sort of think about that, what we're interested in is we're interested in defining and identifying what we call the seizure onset zone. Not the region that goes through seizure, but the region that initiates the seizure. That's sort of a critical point, that it may be a population of neurons that actually initiate the seizure, and it spreads among a bigger population of neurons that leads to a seizure. That's one. Another one that we're interested in is this idea of predicting the onset of seizure. Basically knowing that there's going to be a seizure in 10 seconds or a minute or some number like that. That is also another open research problem that we're interested in. And the last one is, part of the title of the talk, is that how can we prevent the onset of seizure? Which you can think of this thing as being the holy grail of our discussion, as how can you prevent the onset of seizure. It turns out that in this list, we have made some good progress in the first item. and I'll talk about that a lot more. We have some interesting initial results in the second item, the item that says, how can we predict the seizure? Remember that prediction is very different from detection. Detecting seizure is much easier. Predicting the seizure is much, much harder problem. And that's the focus of some of our conversation today. And the last thing I want to say is that, yes, sir?
When a person has a seizure, are they not at some level aware they're about to seize, like, tunnel vision or something before the seizure actually initiates?
Yes, some patients, not everybody. Some patients have learned on their own to feel that a seizure is coming, and that's a very lucky thing for them because they can sit down or they can stop driving. And as you may have heard, there are canines that have been trained to some extent with some success to also help predict the onset of seizure for epileptic patients. And that's the only two things that I know about. But for many, many patients, for them to know that the seizure is happening is not trivial for them. All right, thank you. Now, in this last one, how to prevent the seizure, we have not even started that yet. But the idea there is that if you can spatially focus and say that these small population of neurons are responsible for seizure, responsible to start and spread the seizure, and knowing that when the seizure is happening, it's possible that you could stimulate that region before the seizure happens. You can stimulate them with a very, very low frequency signals, and that feature is called long-term depression, meaning that you're going to depress that area that is about to be excited. Kind of makes sense, but at this point, it's just a conjecture. We have not gotten to that far yet. All right? Now, in all of these things, I'm going to talk about the first one first, where we have more results. Now, the question is that how are we going to get data? How are we going to focus on a particular region that we know is going to be the region of seizure? Right? There are different modalities to record. Deep brain stimulation, deep brain recording is one that you could insert an electrode, especially when the seizure region is deep in the structure of the brain, deep down close to hippocampus or some areas like that. That would be one modality. Another one would be to remove the skull, put electrodes on the surface of the brain, and on dura or on the lead dura, and then close the skull, and then have the patients be in the hospital for a couple of weeks and record from their brain, and then try to learn the focal region where the seizure happens. This happens in the hospital all the time. In a particular ward, in a place in Houston, for instance, there will be 5 to 6 patients going through this exercise. The reason they go through the exercise today is to learn what region of the brain is epileptic and resect that region. And you can imagine that resection, when it comes to the brain, is never, ever a great idea, a good idea, because a region of the brain is never responsible for one function. They're always responsible for multiple functions. And no matter how small the region is, it is going to have long-term negative effect on the patient. Now, our idea for now is that to work with neurosurgeons, try to use this technology to learn the region that spreads the seizure and the region that, and predict the seizure, basically, from the data that we're going to get for these kind of patients. All right? And then this last option would be very, very non-invasive and very comfortable for the patients. The problem with that, as you could imagine, is the signal-to-noise ratio. The fidelity of the signal that we're going to get from this particular modality is going to be very poor compared to these two. But of course, there is the balance between how invasive the procedure can be and the quality of the recording you're going to have and the quality of the understanding you're going to have about the seizures. Now, in the result that I'm going to talk about, and in our work, we have focused on these two. Most of our work has to do with these kind of electrodes called ECOG electrodes. And because some cases, we will have deep brain recordings as well, right? Now, what I'm going to be talking about is that we have about data for about 12 patients that have been in the hospital for a week or two. And in that hospital, they have electrodes like this, and we're going to have recordings from about 150 to 250 electrodes placed on the surface of the brain and record from them. And these recordings are not recordings of the neural spikes. They're recordings from population of neurons, and they're referred to as local field potentials. They look like time series, basically. Right? And this is the actual device that does the recording. And this is a typical recording signal that you can get from epileptic patients. And the one that I've pointed out in particular here is a patient, and I'm only showing 30 channels out of the 150 or 200 channels, and over a time period. And if you notice here, these are not spikes. These are recordings from population of neurons, and therefore from spikes from, let's say, 1 million neurons or 10 million neurons. And you could imagine that in this particular case, the patient was in a comfortable position, comfortable state, and then in this region over here, the patient went through a seizure. That's what we can all guess that this is the case. Went through a seizure, and therefore the activities was hyper-excited. And then somehow over here, the seizure ended, and the patient went through a post-seizure state. And for many patients, post-seizure is a calm state, that they are in a daze and they are kind of not all together, and then they are sort of functioning at half speed, basically. Yeah? And the question that we have is that if we have this time series for days and days and days, how can we learn from the time series? And how can we predict the seizure or focus on seizure onset zone and technology like this? Let's focus on just a few electrodes, just for now. If you think of this like this, you imagine that the green time series is not in the seizure zone, that is just going through normal activity. And you can also imagine that the red and the blue channels, the red and blue electrodes, are basically in normal state till they hit a seizure, right? And they go through a seizure. Then the question then is, between these two, which one of them initiated the seizure, and which one followed suit and went to a seizure state, right? In this particular example, you could imagine, or I can try to convince you, that the red one is the one that initiated the seizure. And then I can also try to convince you that the blue one, the red electrode, the red population, basically got the blue one excited and brought them into a seizure mode. All right? That's not hard to convince you. All right? And we want to find these systematically. Right? If you show this thing to a neurosurgeon, sorry, to a neurologist, that's probably what they're going to say. They're going to say that the green one was just not involved in seizure, and the red and blue one had that kind of relationship. Then the question is that can we systematically find out that the red caused blue to go into seizure? Right? It turns out that understanding causal relationship among time series, these are time series, is a well-studied problem. Right? People are interested in that, and they've studied that for a long, long time, and that's basically exactly what we are interested in. Right? Determining the seizure onset zone. Now, this whole concept of causality is, yes?
How similar are two seizures between each other? So do they have the same, I guess, series of like triggers, or are they dramatically different?
What we understand is that patient to patient, seizures are very different. But another thing we understand from neurologists is that for one patient, two seizures are very, very similar. That's our understanding. And that understanding is also supported by the data that we have from patients that are in the hospital, and some of them hopefully would have, let's say, 3 or 5 seizures, so that we can see the different manifestations of the seizure in those patients. I'm saying hopefully because it's good to know. I mean, if the patient is in the hospital for a week and has no seizures, that is not a good outcome after they've gone through this invasive process. You could imagine that, right? And that's why in those hospital wards, they put a disco light on the last couple of days to induce seizure in those patients, so that this whole exercise was not a waste of time or funding. Now, basically, that goes back to the idea of time series and how can one time series forecast another, right? You can imagine that that is not a new problem. It's been around for a long time. And many people in economics, in transportation, very different fields, have been very interested in that, all right? And for those of you who are in this broad area, you recognize Norbert Wiener's name. You may recognize Granger's name. And these are very well-known mathematicians and econometrics that have worked in this area for a long time, all right? And then this area then was discussed further and further. Granger got a Nobel Prize in that space for his Granger causality formulation. And then others have revisited this problem and had an information theoretic twist to the same problem. You can imagine, those of you who are fans of information theory, you recognize that this whole time series and dependencies and predictions could have an information theoretic interpretation. And it does, and that's pretty fascinating, right? Now, if we go in that direction and look at the information theoretic view of this thing, we get some advantages. The advantages is that information theory is a very universal toolbox that applies to almost any statistical framework, whether your data is Gaussian or not Gaussian, discrete, continuous, it is very universal. And if a concept like causality can be cast in an information theoretic setting, then you can take advantage of many of the information theoretic tools that we have out there to try to formulate the problem, all right? And that's what people have done. They have come up with a concept called directed information, which is different from entropy and mutual information, and it is formulated like this. Basically, you have a time series here, and you're trying to find out, does this time series cause this time series or changes this time series or not? What is the relationship between them? What is the causality between them, all right? It is this definition of a whole time series and another time series, one causes the other, how much information is about X. The nth sample of X is in the nth sample of Y and the past of Y, right? That's basically the idea. And counting and adding them up as you go through your time series. Therefore, you get a measure of how much information X has that imposes on Y, right? This is called directed information. It's been around for a few years now. And then for those of you who are comfortable with mutual information as another concept, information theoretic concept, that has been used widely for the last 60 years or so, the difference between them is subtle. This is mutual information between two time series. And this is directed information between two time series. The difference is in that one little index here, that in the mutual information, it looks at the whole sequence across time, and then looks at the common information between them from this whole sequence and this other sequence, adding them up one at a time. But directed information counts as one sample at a time, and it looks at the causal relationship between them and adds them up across the whole time, so that you could see if one causes the other or not, right? And that's the definition, and then you can rewrite it very simply in terms of entropy, which is some concept that you all know, and this is causal entropy, a little different from conditional entropy. And then basically, at the end of the day, if you have two time series and different realization of these time series, you can compute the causal information between them in this way. And then the question that you may ask is that how does it relate to other causality concepts out there in the literature? For instance, Granger causality. Granger causality has been around for a while. It turns out that if this was used for time series that are Gaussian and linearly related to each other, this number would be exactly some scale times the Granger causality. Therefore, they're very related. The difference being that this is very universal, could be used for any kind of time series, where Granger causality is only measures it for the case of Gaussian data and data when they are linearly related to each other. Therefore, this is much more powerful, much more universal. Now, then all that left to be done is to compute these entropies from the data and then put it together to get the causal directed information among one time series to another. That means that in this picture that you remember from before, if I can get the joint density between these two time series, get the entropy and the causal entropy and all of that, I can compute the directed information between one time series and another time series. That would be a measure of their causality. All right? And then when you have that as a measure between two time series, meaning measure between two electrodes that we have implanted, then we can create a graph that we all love to deal with our data. These are the electrodes. Each of them now have become a node in my graph. And the line between them is the directed information between one node and another. And then if the directed information between one node and another is very small, then there is no line between them. And if it is above some threshold, there is a line between them. And these lines all have arrows. That means that this electrode has time series that causes that one to behave the way following the first one. Right? And then we can take our time series and turn them into a graph. And then know the graph for our electrodes, and then see what we can learn from them. All right? Now, as I said all of that before. And then ictal basically means, let's say in this context, means seizure, let's say. And this would be the graph before the seizure, right before the seizure. This would be the graph during the seizure, and this would be the graph after the seizure. The question then is, can we use this graph to find out what nodes, what electrodes are responsible for starting the seizure, for initiating the seizure? With this graphic theoretic analysis, we should be able to have some measure of that. And the one measure that we worked on is called net degree of a node. These are directed graphs from our data, and then we can define out degree and in degree and the difference between them, and we call that the net degree of this particular graph and this particular node. And then you could summarize this and say that in the pre-ictal period, these electrodes, these nodes, had a very large outflow degree, basically thinking that those may be the nodes responsible for spreading the seizure. All right? Now, in this area, there is no ground truth, right? Because these are all experimental. These are all real patients, real data from the patients. Therefore, there's no ground truth. And our ground truths are our neurologists. The neurologists that we work with have years of experience dealing with data, and then they have their way of identifying seizure onset zone and spread of the seizure and all that. And then all we can say that we identify these systematically through our protocol, and then we had almost perfect match with the neurologist. And we missed one or two in different patients and all that, and then when we work back and forth with the neurologists, they would say, yeah, that could be part of the seizure onset zone also. Therefore, their analysis is all based on experience, and our analysis is based on the data and the threshold and all that, and therefore, we are very comfortable with the matches that we had with a typical neurologist. All right?
What's the fidelity of these snapshots? So the flow between the nodes.
The fidelity meaning that the measure of the directed information, right? Therefore, we do null hypothesis to make sure that when you shuffle things around, the measures stay and they are consistent. That's the best we can do in terms of, because there's no ground truth and all that. And we have examined this concept with respect to some nonlinear relationship of the data that you could synthetically generate. For instance, some chaotic signals that have nonlinear relationship between them, and we've used this metric to make sure that we can predict their causality as well. And then when it comes to this real data, the only thing you can do is do p-value and null hypothesis to verify that your numbers are above some threshold and they're valid. We have done all of that already. Yeah. Yes?
How do you transform the local field potentials to define information? Do you use like band power or coherence or some rate of spike activity?
None of that for now. I'll get to coherence in a few minutes. All we do is that we have time series, right? And then we window them. And then we have multiple windows. And then we use each window to give us the estimates of the joint densities and the entropy and all that. And then we don't do spike sorting. We don't do any of that. We don't look at a particular band yet. We'll get that in a minute. Therefore, it's for the whole time series. The only thing we do, obviously, is to make sure that we get rid of 60 hertz and 120 hertz and 188. That's all. That's all the pre-processing we do in this context. Good question. Did I answer your question? Yes, you did. All right, good. Whew. All right. Now, and that's where we are. We can identify what we call seizure onset zone. And then the question is that now, if you remember, we had 200 electrodes that generate 200 time series. And let's just say that out of those, roughly, 30 of those electrodes are involved in a seizure. And out of those 30, let's say 6 of them, just for now, are seizure onset zone. That means that they initiate and they spread the seizure. Therefore, right now, we can focus on those 6 electrodes as electrodes that are spreading the seizure. Therefore, the game plan would be see if we can look at those 6 electrodes, 6 time series, and then if we can predict the onset of seizure. All right? And you can imagine, as I said before, this is not an easy problem. People have been interested in that problem for a long, long time. And it is sort of similar to trying to predict earthquake or things of that sort. It is a hard problem, but let's think about it for a second. The point of this prediction is that in the period that we call interictal period, which is a long period between seizures, epileptic patients have these little spikes called interictal spikes, right? Interictal spikes, right? Those are believed to be spikes that never became a seizure. They started it and then they ended. They never got that hyperexcited state going. Or that's the conjecture that we read in the literature. And normal people like you and I, we don't have these interictal spikes because we are not epileptic. But the conjecture is that only epileptic patients have these interictal spikes. And the other conjecture is that these interictal spikes have a pattern, and then as they get closer to a seizure, the pattern changes, and then more of these electrodes that are involved in the onset of seizure become coherent, goes back to your question. They become coherent at a particular frequency, and that is a good indicator of the onset of seizure, temporal onset of seizure. And for that reason, we decided to think of it like this, and they focused on these in these areas before the seizure, obviously, because we don't know where the seizure is happening, and then focus on coherence among these channels and see how many of them have become coherent, and then that could be a good indicator for us to see if we can predict seizure. Just going back to this picture that we have seen before, this is the interictal period that we like to focus on. Interictal period that we like to focus on. And we wanted to consider these interictal spikes. And we wanted to be able to have a strategy that would look at this data and in real time compute a feature from the data and then puts that feature and looks for anomalies in the feature so that you could say the seizure is happening or not. That is our game plan. Right? How am I doing in time? 20 minutes, perfect. All right. Now, this is the game plan that we would like to come up with a machine learning pipeline. Machine learning is basically signal processing, right? It's signal processing pipeline, but machine learning is much more sort of a sexier term to use these days compared to signal processing. And the pipeline is supposed to extract features and look to the features and then come up with ways to predict the onset of seizure or not in the next few seconds or so. And that's our game plan. One game plan is that. The other game plan that we have that are working in parallel is that what we're dealing with here is a nonlinear dynamical system. For sure nonlinear and very much dynamic because the signals evolve and then it goes from one kind of evolution to another kind of evolution, pre-ictal, and another kind of evolution that is ictal. And the question is that can we learn from the dynamics and get some features from the dynamical system underlying the system and then use those features to predict seizure? These are the two strategies that we are considering. Today I'm going to be able to only talk about the machine learning pipeline for now. All right? That's our game plan, and this is our pipeline. Right? Basically, start out with ECOG data, the data that we saw before, already focusing only on channels or electrodes that are involved in seizure onset zone. Therefore, already using the techniques that I mentioned earlier to focus on those. And then we have, let's say, n time samples of them. All right? Therefore, we have that much data. And then we want to focus on features. The features we're going to focus on is coherency at a particular frequency that we learn from the literature that is involved in getting electrodes and populations to be in sync right before the seizure. Right? Therefore, we're going to extract some features. And then from those features, when they are in sync, we're going to focus on only one of the electrodes. They basically look for concepts like eigenvector centrality. If we turn that into a graph, focus on one element of the graph, and then use that one element of the graph, one time series, and put it through some kind of a anomaly detection. They call it one-class classifier. All right, these are just some standard pipeline that you could put together just thinking about this problem. And we're going to do that. We're going to see how it works. All right? Now, eigenvector centrality is very standard. In a graph, you can find out which is the most important node of a graph. Easy. Pre-processing, you can think about things like wavelet denoising to try to reduce the noise and all that. This is in addition to getting rid of 60 hertz and 120 hertz. The feature is going to be the coherence that I talked about before. And let's just talk about that for a second. And then the S1 class SVM is off the shelf, pretty standard by now. All right, we can just use it off the shelf. Now, let's talk about coherence among the channels that are involved in seizure onset zone, focusing on a particular frequency, right? Some gamma frequency or high gamma. The concept of coherence between two time series has been around for a while and has a very nice definition when the time series are stationary and Gaussian and all that. They have a beautiful definition. Definition of coherence between two time series is the cross power spectral density at that particular frequency divided by the individual marginal power spectral densities at that frequency squared and all that, right? This is called the coherence between two time series that are linearly related and Gaussian. But as we know, our data is not Gaussian and they're not necessarily linearly related to each other. Then we go back to information theory. See what can we do in that space now. There is a concept in information theory, mostly due to Berlinger at Berkeley, that has been working on this area. And he found out that coherence can be related to mutual information between two time series in the frequency domain. All right? Very kind of neat concept. Basically, he showed this equality for the Gaussian case. That enabled us to define coherence for cases that are not Gaussian. As long as you can compute the mutual information between two time series at a particular frequency, then you can get the coherence between these two time series through this relationship. All right? Now the question is that how can you get mutual information at a particular frequency of two time series? All right? And that is nice because you can take the time series, put them in the spectral domain, do the Fourier transform of that time series. In this case, the Fourier transform is not ordinary Fourier transform, is what we call Serge's Fourier transform. Basically, d of x tilde are a Fourier domain version of the data. This is the data, and this is the data in the frequency domain of the same data at the particular frequency. All right, we can compute those. We can transfer the data, put in the frequency domain, and then learn and compute the mutual information between those two now time series that have been indexed in the frequency instead of time. All right, the rest of the pipeline is trivial. All right, we take the data, the same data that we've been working on before, different frequency time series, put them through this kind of a fancy DFT, basically Fourier transform dealing with random processes like this, and then put them in the frequency domain and compute the mutual information between these two time series in the frequency domain at that particular frequency. And then that would give us the coherence between these two time series. All right? You can do that. We have done that. And this is how it's going to look like. All right? Basically, this is different frequency bands averaged over channels in the seizure onset zone. This is before seizure. You see that there is a lot of coherency in the high gamma range. This is during seizure. That spreads out a bit longer. Coherency spreads out across a larger set of frequencies. At the end of the seizure, the post-ictal, when the patient is very calm and done with the seizure, the coherency is at the lower frequencies. And this is the progression across different time periods of this particular analysis. All right? And then what you can do then is create another graph. This time, same kind of electrodes, except that the line between them is not directed anymore, because these are the coherency between them. And that shows that the pre-ictal coherency at some range of frequencies, during the seizure, coherency among some electrodes, and post-seizures. Then what this can do, this can give us the features at this point, and you could put the features, then you can get the graph and identify the most important node of the graph, and then make an anomaly detection for that particular node when you have already reduced the dimensionality of the problem. Right? As I said before, we are still actively working on that. It has been very successful in terms of perfect prediction performance. In all of our patients, having each of them 3 to 5 seizures, we've had perfect prediction probability. A few, something like 45 seconds or a minute before the seizure, we can predict. But the problem is that we still have high false positive rate. And that is the point that we're still looking at, trying to, yes?
If your graph is undirected, how do you know the starting point of the seizure?
Now remember that here already we are focusing only on regions that are responsible for onset of seizure. We have 200 electrodes. We go down to 30 that are involved in seizure. We go down to 6 that are involved in seizure onset zone. They're responsible to spread of seizure. Among those, we're going to try to find the one that is the center of the coherency among them. And that's the one that we pick. Good question. And all we have done is, it works. It has a high false positive rate. And we are still working on that. As I said, it is some initial result that is promising, but we are not done yet. And the group of undergraduates put this thing in hardware. Where is the hardware? There was a hardware that I showed earlier, somewhere in here. Yeah, that piece of hardware right there. This algorithm has been put in this hardware, and there's still a long ways to go for implementing it, but it's been done already. And the goal is still the same, that you would like to find a way, a protocol to identify seizure, to predict seizure, and put into hardware for implementation. And another one that I just want to spend 1 minute talking about that is a parallel effort that we're working on this. We are so fascinated with the nonlinear dynamics of our brain, and we've been interested in trying to understand the underlying dynamical system of our brain. And whenever you deal with a nonlinear dynamic system, you know that is a very complicated system to understand. There are a lot of nice techniques out there that take your nonlinear dynamical system and they embed the system and create a much bigger linear system with much, much larger dimension, linear system that approximate that your nonlinear dynamical system. And then those much larger linear dynamical system, you could do dynamic mode decomposition of that, trying to understand the dynamics of that big nonlinear system that you started out with a nonlinear and then extended the dimension to a much larger linear dimension. And then you could do things like dynamic mode decomposition or SVD and try to see if your linear dynamic system can approximate your nonlinear system. And this is one result that I'm going to show. It's hard to read even here. All right. Either the red or the blue is the actual dynamical data that we get from our recordings. And the red is a linear approximation in a much larger dimension of that nonlinear dynamics. And as you see in this plot, this is for seizure onset zone again, right before seizure. And as you can see that the linear system beautifully approximates the nonlinear system. Therefore, you have a whole set of eigenvalues, eigenvectors, and modes of the system that approximate the nonlinear system. Then you could use them as features and investigate this in the interictal period, pre-ictal period, ictal period, and come up with a feature that you could use with this approximation to help you predict. All right? And that's what we're working on now. With that said, this is the end. I just want to remind you what we're working on. All of these projects are in progress, and I just wanted to share a snapshot of where we are with you. I'm done.
Thank you. Thank you. Thank you. So we have time for questions.
Yes?
You mentioned you have a high false positive rate. Are we talking like an order of magnitude larger, or?
We have now about 3 false positive an hour.
And that's for patients that are having how many seizures per hour?
One a day. Yeah. It is high. We are not happy, and we haven't published this work because it's too high. But the point is that we were less worried about false positive than we were with probability of detection. The reason is that even if you have too large of a false positive, the result could be that the patient stops driving way too often, but it still could be a positive thing for the patient, but it's a work in progress. We're trying to reduce the false positive. By trying to understand a specific of a patient and try to sort of adjust the pipeline for each patient. Because the pipeline that you saw, the pipeline itself was generic for all patients, but then when you implement different pieces of it, it becomes specific to the data that we have. But we're also thinking that these kind of pipeline could be adjusted specific to a particular patient when we observe the patient. And maybe that way we can really reduce the false positive to, let's say, 1 a day as opposed to 3 an hour. It's not an easy problem, you can imagine.
Any other questions? Yes.
Do you have any plan to go beyond predicting to countering using your predictions?
Yeah, I mean, that's the holy grail, is to predict and be able to stimulate so that you prevent. That is our ultimate goal. We're not there yet.
Any other questions?
Yes?
Do you think with higher resolution, like neural spiking data and LFP data from plant to microelectrodes, you have a better prediction?
Yeah, I can only imagine so. I was talking to Aazhang, one of your colleagues here today. She's building microgrid ECOG electrodes, which much higher resolution, and like her electrodes are each like 40 micron large. And you can imagine that with that you get much better spatial resolution, and some of this could be quite useful. We don't have that. I can only imagine that. Yeah.
All right, let's give our speaker a hand.
Thank you.